Hello, Mr. Betts here. Let's take a look at a few examples that have to do with the extreme value theorem and critical points. So the first one, we have a function that's defined on a closed interval. So every x value on that interval, we can plug into the function and get a y value. It satisfies this equation here. So the two endpoints are going to have the same value as each other, and it's going to have the same value as the function at 1/2. And then the last one is that on the open interval from 0 to 1, f is strictly increasing. So what that means is for any x value to the right, the value of the function is going to be greater than any x value to the left. So if we pick two x values, the x value on the right is going to have a greater function value than the x value on the left. So which of the following statements have to be true for the function on the closed interval from 0 to 1? So what I would do for this is draw a picture. So if I graph what this could look like, so some things that are going to have to be true is that f of 0, f of 1/2, and f of 1 are all at the same y value. And then the next part here says that if f is strictly increasing on the open interval, I can't start at the endpoint here and do something like this because then we have an x value here that is smaller than an x value here. So to satisfy that strictly increasing on the open interval, I'm going to have to start at some point lower than the endpoint so that I can increase through that point at 1/2 to all the way to 1, but not including 1. So we're going to get something that looks like this. I do want to point out that it could possibly look like, I don't know, this. That would satisfy this also, but I'm going to keep it a little bit simpler and just say that it is continuous on the open interval. This meets all the criteria, and it minimally meets all the criteria. So we could have some more fancy stuff in there, but it's going to look something like this. So A says f attains both a minimum and a maximum value. This is the conclusion of the extreme value theorem that has to be true if a function is continuous on a closed interval. Well, based on the stuff that we were told about f, this is not a continuous function on the closed interval, so the extreme value theorem doesn't guarantee anything. And in fact, B and C are also conclusions of the extreme value theorem. It's just specifically minimum and maximum separated, where the extreme value theorem guarantees both. So really, A, B, and C are all the conclusions of the extreme value theorem, which doesn't apply here because this is not a continuous function on a closed interval. That leaves D as the only possible answer. But looking at the graph that we ended up with, you can see that if we look at the left endpoint here, as we increase from the left endpoint, all the values of the function are going to be greater than that open point at the left endpoint, which means that this cannot be the absolute minimum on this interval. And likewise, we don't get an absolute maximum to the right endpoint because we have that open point there. So this function does not have a minimum or a maximum value on the interval. So the second example here, we have g as a function given by g of x equals x squared times e to the kx. So k is just going to be some number, some constant. And what value of k then gives us a critical value at x equals 3/2? So what we want to do is take the derivative of this, and we'll just pretend like k is some number, and then we'll figure out what our critical values are based on what k is, and then solve for k. So we'll start by taking the derivative. Remember, critical values is going to be where the derivative equals 0 or is undefined. So taking the derivative here, we have derivative of the first times the second plus the first times the derivative of the second. The derivative of e to the kx is going to be e to the kx times k. So we're using a chain rule there. The derivative of k times x is going to be k, just like the derivative of 3x is 3. Then we do want to set this equal to 0. And to solve that, we're going to factor. So looks like we can factor an x out. Looks like we can factor e to the kx out. And then what's left is going to be 2 plus k times x. And then that's still equal to 0. So now what we're going to do is we are going to set each of these equal to 0. This is going to give us a critical value at x equals 0. E to the power of anything can never equal 0, so no critical value there. And if we set that equal to 0, we're going to get x equals negative 2 over k. Now we're looking for where this is going to have a critical value at 3 halves. X equals 3 halves, so we're going to set that equal to 3 halves. So we'll say negative 2 over k is equal to 3 halves. And then solving for k, we're going to get k equals negative 4/3. You can do that by cross multiplying and then dividing by 3, and that's going to be your answer.